Welcome to our class on computer architecture and instruction cycle. Today we'll be diving into fundamental concepts that drive the operations of modern computers. This knowledge is crucial for understanding how computer process information and execute programs. Organize entirely the principles behind the architecture and the step-by-step process of how instructions are fetched and decoded and also executed. So we'll look at that. So let's start with the basic. A computer system consists of four main components, which we have talked about previously. The CPU, which is the brain of the computer, performing calculations and controlling other components. Then we have the memory, specifically RAM, which stores data and instruction temporarily. Then we have the input and output devices. We allow the computer to interact with the outside world. Then we have the system buses, which is actually connects all the components and allow them to communicate. So these are actually our system buses over here. These are the system buses. Then we have the CPU, the input device, and the output unit. Then we have our storage device. In von Neumann architecture, proposed by John von Neumann in 1945, forms the basis of modern computer design. Its key features is the stored program concept, where both data and instructions are stored in the same memory. This allows for flexibility in programming but can create a bottleneck known as a von Neumann bottleneck, where the system bus can become a limiting factor in performance. So this is actually the von Neumann architecture, which is actually the concept we actually used in our modern day computing. There are a lot of architecture that came out over the years, but this is actually the most one that was adapted. So where we have our CPU and memory, they use the same memory to store. That's why you have our LO1, LO2, and which we'll be looking at later in the course. So this is actually a memory that it says data and instruction should be stored in the same memory, where so that it will allow for flexible computing and also making our processes more faster. Now let's zoom in on the CPU. It consists of three main parts. We have the control unit, which manages and is the execution of instructions. We have the ALU, which performs mathematical and logical operations. Then we have the registers, which are very small, fast storage locations within the CPU for holding data and instructions temporarily. So whatever data or instruction that comes from the RAM goes to the registers. So the registers are what holds the information. Then so the inner CPU, we have the control unit, we have the registers over here, which is actually the processor, and we have our main memory. So this is actually the combination logic is where it's also known as your arithmetic logic unit, where your arithmetic operations is going, your plus, addition, your binary calculations, all those things. That's where it's going on in the CPU. That's where the CPU does those calculations. Then we'll look at the fetch, decode, and execute cycle, also known as the instruction cycle. It is the basic operation cycle of the computer. It consists of three main stages. We have the fetch stage. The next instruction is retrieved from the memory. Then we have the decode stage. This instruction is actually interpreted by the control unit. Then we have the instruction that is carried out, which is the cycle repeats continuously as long as the computer is running. So this cycle keeps on repeating. It will execute the instruction that was coming. Execute it, and this keep on running as far as the computer is actually running. And during the fetch stage, what's happened in the first stage? The program counter contains the address of the next instruction, and the address is copied to the MAR, which is the memory address register. The instruction of that address is retrieved from the memory and actually placed in the memory data register, which is MDR. Finally, the instruction is now copied to the instruction register. The CPU is then incremented to point to the next instruction. So the PC actually knows, oh, this is the next instruction you need to take. After something that was say, I'm just okay, take this one, this is the next one. So this is actually what the fetch stage does. Then we have the decode stage. So the control unit now interprets the instruction that came in from the IRO. It determines what operation needs to be performed and what data, which is operands, are needed. So what is the operand? Operand is the addition, is it addition, subtraction, or multiplication, whichever data is need to be operated on. Then if operands are needed from the memory, he has to fetch it from the memory during this stage. Then if it's not, it will actually execute it on it. You actually work on it on its own. Then the control unit prepares the necessary control signal for the execution stage. So this is actually, it will now prepare the control signal for the execution stage. Then we have the execute stage. It is where the actual operation takes place. The ALU performs the calculation for data movement and instruction. Then data is now transferred between the registrars or between the registrars and the memory. So either it is actually the registrar that will work on the data, or the memory and the registrar. Then the program flow instructions like the jumps or branches, the PCU may be modified, just like maybe, okay, save this and do this, change the settings. So this is where those instructions can now be modified. The results of this operation are typically stored in a registrar or on a memory location. Now, instructions can be categorized into several types. We have data movement instructions. These are the ones that transfer data between registers or between memory and registers. So that is data movement instruction. They transfer information between registers or between memories and registers. Then we have arithmetic and logic instruction, which perform calculations or logic operations. So these arithmetic and logic instructions, they perform calculations or logical operations. Then we have control flow instructions. They alter the sequence of instruction execution. So this control flow instruction, they alter the sequence of how the instructions are actually executed, either jumps or branches. Then we have the IO instructions, which is input or output instruction. They handle both input and output instructions. Now is ISA, which is instruction set architecture, is the interface between the hardware and the computer and the software. It defines the set of instructions that a processor can execute. So there are two types of SIAs. They have the CISC, which is complex instruction computing, set computing, which has its own specialized instructions. Its own instructions are specialized. Then we have the RISC, which is the reduced instruction set computing, which are smaller set of simpler instruction. But the popular ISAs include the x86, which is actually the one they call 32-bit, which is used in most desktop and laptop. Then we have the ARM, which is mobile, for mobile devices. Like you have the ARM and the x86, 86, which are actually, we also have the x64. So the x86 is actually 32-bit instruction. Then we have ARM, which is for mobile devices. Pipelining. Pipeline is a technique we use to increase the instruction throughput. It actually involves breaking down an instruction into smaller bits to be executed in parallel. For example, while one instruction is being executed, the next one can be decoded and the third can be fetched. So this increases the overall performance by introducing challenges, introducing challenges like pipeline hazard, which need to be managed. So while he's working on this instruction, the next one is pipelined, sent to be decoded, third one is sent to be fetched. So this is actually how your instructions take place in your computer system. We have modern processors. So modern processors advancement. So the modern advancement we have is modern processors uses advanced techniques to improve performance. They have superscalar processors which can execute multiple instructions simultaneously. They have out of order executions, allows instructions to be executed as soon as their operands are ready, rather than in a strict program order. So instead of in a program order, this. So anyone that is ready, it executed. So that is out of order execution. Then we have the advancement in them is actually branch prediction, attempt to gauge the outcome of the conditional branches to keep the pipeline full. So it actually checks which one is the prediction that will actually work well. And if it detects it, it just executes it so that the pipeline will be full and it will be processing information faster. Then to summarize all we have talked about, we have covered the basic organization of computers. We have talked about the von Neumann architecture. the fetch and the code, execute cycle, the types of instruction we have, and some advanced concepts in modern processors. Understanding this fundamental is crucial for anyone working with computer, whether you are developing software, optimizing performance, or even troubleshooting issues. So all these things are actually very important to know. So if you have any questions to conclude our lesson on computer organization and instruction cycles, if you have any questions, you can actually drop down. We'll explain more better. And I recommend that you guys actually go find resources on computer architecture or assembly language programming. This will give you a more hands-on understanding of how instructions are processed at the lowest level. Um, Thanks for watching, and I would love to see your comments or your questions. Thank you. See you in the next class.